As you can see, it's divided into two parts. The first part will deal basically with theory. We'll look at some luminescence terminology and theory. We'll then look at two common interferences to all fluorescence instruments, basically Raman and Rayleigh-Tyndall scattering. We'll look at how molecular structure and environmental effects affects photoluminescence. And lastly, in part one, we'll look at the fluorescent instrument itself. Part two will deal mainly with applications. First considered will be the instrumental correction, which is necessary for the determination of quantum yield, and we'll look at both relative and absolute methods. Lastly, we'll look at synchronous scanning and how it relates to three-dimensional fluorescence spectroscopy. One of the ways that we perceive the world around us is through our eyes. This slide here shows you the various ways our eyes can receive information. The top line shows the direct emission of light. It's the sun, fluorescent lamps, incandescent lamps, light-emitting diodes, all emit light directly, which strikes our eyes. The bottom line shows the other way. One of these illuminating sources shines on something. Here we take the sun shining on a rose, and then that light can be reflected or photoluminesced back. Photoluminescence or fluorescence and phosphorescence can be part of that red arrow that affects the color along with reflection of an object to our eyes. We're going to stop here for a second and talk about terms. Words are important, and unfortunately the terminology of fluorescence tends to get misused and confused. So I've outlined it here. First, luminescence is a very general term that simply describes something that gives off light. Photoluminescence is a specific type of luminescence that first requires the absorption of light by a molecule or an atom, and the light then gets re-emitted as either fluorescence or phosphorescence. Fluorescence is derived from the singlet quantum state and is characterized by very short emissions in the nano and picosecond time frame. Phosphorescence arises from the triplet quantum state and is usually much longer lived, in the order of hours to milliseconds. Finally, chemiluminescence is luminescence that derives its energy from a chemical reaction, much like the light sticks and necklaces you see kids playing with after dark. And finally, bioluminescence is chemiluminescence that occurs in a living system. So when we talk about photoluminescence, we're talking about electrons and electronic energy states. These energy states can be in atoms, or they can be associated with the molecular bonding structure of molecules. Very simple. Light goes in and promotes an electron into a higher energy state from the ground state. Like all good things that go up, eventually it has to come back down. And the electron can come back down from the excited state to the ground state and release that energy in two ways. It can release it as photoluminescence, either fluorescence or phosphorescence, or it can jiggle the molecule around and create molecular motion and release that energy as heat. Okay, everybody take a deep breath and we'll do a little bit of quantum field theory. You see here a Jablonski diagram, which is a diagram of the energy states inside the bonding of a molecule. You see we have a ground state, we have an excited singlet state from fluorescence, and we have an excited triplet state for phosphorescence. Notice that all three of these states contain smaller energy vibrational levels, and they're rather important. The blue items are items that involve a photon either being absorbed or re-emitted. The red items are involved in radiationless transitions. In other words, they're involved in producing heat. So now let's take a look at each of the three interactions we have here. First, absorption with no photoluminescence. The electron goes to 1, back down through 4 to the lowest vibrational level of the singlet state, across through 6, an internal conversion, and then back through the ground state to number 4, and all this energy is being released as heat, not as light. For fluorescence, you go from 1 to 4 again to the lowest level of the excited state, and from there you have now the emission of a photon, which is number 2 for fluorescence. For phosphorescence, you go from 1 to 4, and now to 5, which is intersystem crossing, again through 4, and then back down to the ground state through the emission of a photon in phosphorescence. So, several things. Note the size of the arrows and the energy. Absorbance at 1 is the largest energy. Fluorescence at 2 is kind of middle energy, and phosphorescent at 3 is the lowest energy. So this is the theoretical basis of photoluminescence. So what do things look like on the output of a fluorometer? Here you see a typical presentation of data from a fluorescence instrument. A fluorescence instrument can measure both the absorption, typically called the excitation spectra, but it is the exact same thing as an absorption spectra that you measure on a UV visible instrument, except when you do excitation on a fluorescence instrument, it's not in absorbance units, it's in fluorescence intensity units. So you see here the absorbance or excitation in blue and the emission in red. Note, as I was talking about arrows and energy levels, light absorption always occurs at a higher energy or lower wavelength than the photoemission. So you're always going to see the excitation at shorter wavelengths than the emission. The offset between the peak of the absorption and the peak of the emission is typically called the Stokes shift. The Stokes shift will be different for different molecules. Sometimes you have a small Stokes shift. The one represented here is relatively small. Sometimes you'll have a large Stokes shift, maybe 50 or 60 nanometers. Notice also, I've said for a single component here in the slide. No matter, this is an important feature of fluorescence. For a single component, a single fluorescence component, no matter where I set the excitation, whether it's at 450, 500, 525, I will always see the exact same emission peak. The emission peak will always be in the same place, but the intensity of the emission spectra will vary with the intensity of the absorbance spectra. If you have an emission peak that is moving around as a function of excitation wavelength, you have a mixture. Here you see a typical hierarchy of photoluminescence relationships. Excitation is usually at the shorter, more energetic wavelength region. Fluorescence is usually in the middle, and phosphorescence is usually at much longer wavelengths than fluorescence because of its lower energy. So this is the way things typically line up for a molecule that can do all three. Now, it's not unusual for a novice fluorescence spectroscopist to put their triple distilled water blank into the fluorometer and be horrified to see that there are actually 2 peaks in the water, and they generally assume that they've got some sort of a contamination. That's not the case. Unfortunately, fluorometers are just as easily measure scatter as they do fluorescence. And particularly Rayleigh-Tyndall and Raman scattering are always going to be interferences in a fluorometer. They are present in any fluorescence instrument, and they are present in just about every single sample. Rayleigh-Tyndall scattering occurs when the excitation wavelength and the emission wavelength are equal, or it occurs at the excitation-emission monochromator crossover. Raman scattering is always offset to longer wavelengths than the Rayleigh-Tyndall scatter, and it is the only peak that will actually move as a function of excitation. And not only does it move, but it gets further and further away from the Rayleigh-Tyndall scatter peak as you move the excitation to longer red wavelengths. And this is because Raman scattering literally is an energy-dependent relationship, not a wavelength-dependent relationship. So it literally moves further away from the Rayleigh-Tyndall scatter peak. You can see in the figure in the upper right, you see the blue, very nicely symmetrical Rayleigh-Tyndall scatter. You then see a fluorescence emission in black, and then right kind of on the upslope is the Raman scattering that's kind of in brown. And at the top, it's kind of buried. The bottom spectra shows you a PBS buffer, which is essentially water, and you can clearly see the Raman band sticking out of the fluorescent emission. You can see the blue water blank. The other thing, both the Rayleigh-Tyndall and the Raman scatter are almost Gaussian in their makeup. They are very symmetrical. Most fluorescence emissions tend to tail into the red. So you can almost identify the Rayleigh-Tyndall and the Raman based on the symmetry of the peak. Now, one of the ways which you can eliminate a Raman scatter interference is by the use of an emission side cutoff filter that blocks the scattered light. One of the unique characteristics of fluorescence spectra is they tend to have a fair degree of vibrational subpeak structure to them, as you can see here with the spectra on the right. They have a lot of detail to them. So we're going to return to the Jablonski diagram on the left to understand this. And you'll notice that the emission spectrum is almost the mirror image of the excitation spectrum. And there's a reason for that. That's because the vibrational levels within the ground state and the excited state, here labeled by the indicator V, the vibrational structure of the excited state is a mirror image of the vibrational structure of the ground state. So here we see in the red the electron being promoted from the lowest vibrational level of the ground state, V0, up to various other vibrational levels of the excited state, and that gives you the peak structure that's in your excitation spectra. The electron then comes back down through heat transfer or non-radiative transition to the lowest level of the excited state. Fluorescence is always generated by the lowest level of the excited state, but the electron can come down into the various vibrational levels of the ground state, as indicated by the blue line. That gives you the detailed structure that's in your emission spectra, and you'll notice the blue arrows are collectively less than the red arrows and have lower energy. So the blue transitions responsible for our emission are always at a longer wavelength than the excitation. And this is what gives rise to the mirror image vibrational structure of the excitation and emission spectra. The unique transition from the lowest vibrational level of the ground state to the fluorescence from the lowest vibrational level of the excited state is typically called the 0-0 transition. And here you see that in the overlap, you can see that is what defines the Stokes shift. The Stokes shift is basically the energy difference between the lowest vibrational level of the excited state and the lowest vibrational level of the ground state. So by now, you've probably figured out that any molecule that fluoresces or indeed photoluminesces must first absorb. So if everything that photoluminesces must absorb, why would we want to use fluorescence as opposed to a UV visible spectrophotometer? And the reason is the two S's that you see here. First, sensitivity. Absorbance spectroscopy's minimal concentration limits are somewhere around 10 to the 5 to 10 to the minus 6 molar. For fluorescence, it can be as low as 10 to the minus 13 or 10 to the minus 15 molar, almost 10 orders of magnitude more sensitive. Indeed, fluorescence is one of the few techniques that is almost as sensitive as radioisotope analysis. Fluorescence is also very sensitive to its surrounding environmental factors, so it can be used as a probe of the environment, much more so than UV visible absorbance. Second is selectivity. Not all molecules that absorb produce luminescence. So if you're dealing with a complex mixture that you want to simplify, you might be able to pick out one or two fluorophores away from all the other things that are simply absorbing and not fluorescing. Lastly, there are two techniques that are unique to fluorescence that allow you to maybe look for a single molecular species in a mixture, or you can use them to characterize complex mixtures like oils, which are composed of a number of fluorescent compounds. We're going to talk about later synchronous scanning and three-dimensional scanning that are unique techniques to fluorescence spectroscopy that you can use to characterize a mixture. So here is the most frequently asked question in the world of luminescence spectroscopy. Someone will call and say, hey, I'm running a given concentration and I get 2,000 fluorescence intensity units. Someone else reported in the literature that the exact same concentration read 100,000. What's going on? Fluorescence intensity units, unlike absorbance units, are all relative. The absorbance unit is a standardized value, though, so 2 absorbance units better be 2 absorbance units on every single UV visible instrument. However, that's not true in fluorescence spectroscopy. The fluorescence intensity unit is both sample and instrument dependent. You cannot compare raw fluorescence intensity units between different instruments. You can't even compare them against the same instrument over time. The main reason for this is as the lamp ages, your fluorescence intensity units will go down. So that means even for a stable sample, you're liable to get different raw fluorescence intensity readings over time. This points to the importance of running a calibration standard for concentration is absolutely vital in real time with your data. You must run a calibration standard every time you run unknowns so that you can standardize the fluorescence intensity value to a concentration. Now, most typical fluorescence compounds contain a benzene ring. In many cases, it's a fused benzene ring. And this brings us to something that's unique to these types of fused benzene ring systems. They have a tendency to stack at high concentrations and lead to what's called concentration quenching. In other words, flat rings, when you get them concentrated enough, tend to aggregate together in large stacks of the planar systems. And this can lead, when they stack like that, it reduces their fluorescence intensity and quenches the fluorescence. So that's why a general rule of thumb is when you're working with these types of fluorophores, you want to work very dilute. By dilute, we mean at concentrations where the absorbance at the excitation wavelength is less than 0.05 absorbance units. Now, you may have noticed in the last slide, as you fused more benzene rings onto a fused ring system, the wavelength of the emission moved towards the red. And here you see most of our fluorescence compounds have low energy pi to pi star transitions, which are typical of aromatic ring systems. You see here the example of pyridine and quinoline. When you add the second ring system onto it, it moves it into the red, and it also increases the quantum yield. Also, substituents are important. If you happen to put something like a heavy atom on there, like a halogen, like a bromine or a chlorine, that will usually quench, called the heavy atom effect, and it can actually promote phosphorescence. But in general, halogens decrease the quantum yield. Also, heterocycles. If your heterocycle can pump electrons into the aromatic ring system, specifically non-bonding electrons like you'd find in nitrogen, this will also enhance the fluorescence signal. Structural rigidity in a molecule is very good as far as fluorescence is concerned. The more you prohibit rotation around bonds, which usually causes the energy provided by the photon to be released as heat. If you can lock that down into rigidity, it will become fluorescent. Here you see biphenyl, which has free rotation around the bond. If you lock it down with the addition of the CH2 group there in fluorine, it does nothing but lock it into place and enhances its fluorescence. Chelation can do the same thing. You look at the 8-hydroxyquinone. If you chelate it with zinc, that causes you to have a rigid ring system, and that will, whereas the 8-hydroxyquinone is not very fluorescent, the chelate is. Now, as you're probably beginning to see, it's very difficult to try and guess as to whether any given molecular structure will actually fluoresce or not. You see there are a number of things that we can make generalizations, the number of fused rings, the rigidity of the molecule. Another thing that's a generalization that works fairly well is adding substituents onto an aromatic ring. In general, electron withdrawing groups or deactivating groups that literally suck electrons out of the aromatic ring will decrease fluorescence. Things like carbonyl, nitro, cyano, and as we discussed before, halogens all decrease fluorescence quantum yield if added to a ring system. However, electron donating groups that pump electrons into the ring system and are activating groups like hydroxyl, amine, amide, alkyl, these will increase the fluorescence of the ring system. As you've no doubt gathered by now, molecular motion or heat is bad for fluorescence. It will lower the fluorescence quantum yield. Therefore, it's no surprise that temperature is a crucial factor in fluorescence intensity. Fluorescence varies dramatically as you change the temperature. Therefore, most fluorescence assays are done at the lowest temperature possible to maximize quantum yield. If you're doing a quantitative analysis, it is absolutely critical that you carefully control the temperature so that it doesn't fluctuate. When you're running your standards and your unknowns, you want to make sure that the temperature does not change so you don't get variation in the intensity with the solvent temperature. Solvent is something else that can change the fluorescence wavelength. Here you see a compound going from an organic solvent to a highly polar water solvent, and this shows you an example of polarization redshift. The more polar the solvent, the more you will shift it into the red. So you may want to watch out for this if you're doing solvent studies. You will see your peak move around as a function of solvent polarity, with it moving to the red with the more polar the solvent. As if there hasn't been enough to consider with all the things that can affect photoluminescence, we're going to finish up with pH. If the fluorescent compound you're analyzing can ionize, you have to be very aware of the pH and control the pH almost as meticulously as you control the temperature. Usually, the ionized and the non-ionized form will have very different emission wavelengths and intensities. If you are operating at a pH that is on or around the pKa or the pKb of an ionizable compound, you're literally working with a 50-50 mixture of two species that have different fluorescence properties. So you need to be aware of your pKa or pKb and make sure your buffer is at least 2 pH, maybe 3 pH units on the other side of that, so you're dealing with just the pure ionized or the non-ionized species and not with a mixture around the pKa or the pKb. When we measure photoluminescence in a fluorescence instrument, it is geometrically different than the measure of absorption in a UV visible. Here you see a typical cuvette with a sample in it. In a UV instrument, indicated by the green arrow, the incident light strikes your cuvette, goes through the sample, and it then proceeds in a linear fashion to the detector. That is not true with fluorescence. When the incident light strikes a cuvette, fluorescence is generated through 360 degrees in a sphere around the sample. Therefore, we do not measure fluorescence in a straight line with the excitation light because of scattering interference. We measure it at a right angle here. The yellow arrow indicates the emission is coming out at, it's just showing it coming out at a different angle than the linear transmitted light. It's actually coming out through 360 degrees, and we measure at a 90-degree angle to minimize scattering interference. Let's finish up part one by talking a little bit about the fluorescence instrument. You see an optical diagram of a typical fluorometer pictured on this slide. It's almost like you took two UV visible instruments and kind of combined them. The excitation monochromator contains the lamp source, some mirrors, a diffraction grating to select the wavelength of light, and it shines the exciting light on the cuvette. The fluorescence is then collected, notice, at a right angle to the exciting light and goes into the emission monochromator, which has similar mirrors and diffraction grating and a detector. So one half of the instrument is exciting the sample and the other half is monitoring the emission. Note that the cuvettes depicted on the right, for an absorbance cuvette, it's typically clear on only two sides, with the other two sides frosted for you to put your fingers on to put it in the cuvette holder. But a fluorescence cuvette, because the fluorescence measurement is made at a right angle to the excitation, is clear on all four sides. So how does the instrument actually scan excitation and emission spectra? At the top here is an example of a typical UV visible where the monochromator scans and the different wavelength light strikes the sample and the transmitted light is measured. On the bottom is a fluorescent instrument. The emission spectrum is a bit more conceptually easier to understand. You basically park the excitation monochromator at a wavelength, say it's 250 or 300, and then you scan the emission side monochromator and collect the wavelength-dependent change in the emission light. To generate the excitation spectra, you hold the emission monochromator stationary, and then you scan the excitation monochromator and change the wavelength of light exciting or striking the sample, and this gives you the excitation spectra, which is qualitatively similar to the absorption spectra.
Thank you, Dr. Taylor, for the first part of the presentation. That was very interesting. Let's look at the questions we've received so far. All right, here's the first question. You didn't say much about slit width. What effect does changing the excitation or emission slit width have on the spectrum?
Okay, that's a good question. The excitation and emission slit widths do two separate things in a ratioed fluorometer. A ratioed fluorometer is an instrument that splits off part of the light intensity of the lamp and has it shine on a separate detector, and this then feeds into the detector to make the instrument stable over time, but it also changes what the slits do when you change them. On the emission slit, if you open up the emission slit, you essentially collect more lights from the sample, so the fluorescence will go up. If you decrease the slit, the fluorescence goes down, so that you can actually use it as a volume control to get a number of fluorescence intensity units that you want. The excitation slit, when you open it, it causes more light to strike the sample, and most people would think that that will cause the fluorescence intensity to go up as well. And it would, but in a ratioed instrument, it also increases the light on the ratioing circuit. So what happens is when you open that slit, the intensity doesn't change much. It may even go down. What is improving is the noise level. You are shining more light on the sample, so your noise goes down with the larger slit. So the best way to think about it is open and close the excitation slit to control the noise, and open and close the emission slit to generate the fluorescence intensity that you want.
Thank you. Let's do another question. Here it is. How exactly do you get rid of the Raman peak with a filter?
Interesting question. I didn't kind of answer that. I just said you can put a filter in to reduce the Raman band. What you want is a cut-on filter. This is a filter that blocks the short wavelengths and allow long wavelengths to pass, and it's usually put in front of the emission beam. So it's blocking the short wavelength light and allowing the long wavelength light to pass. What you want is a filter that has a cut-on that is longer than your excitation wavelength, but is shorter than your emission wavelength. You don't want the filter cutting off any true emission peak. So your cut-on filter needs to be somewhere in between, longer than your excitation wavelength and shorter than your emission wavelength.
Thank you. Let's do one more question before we move on to part 2. Here it is. How much of a problem is pH, and how closely do you need to control pH?
It's a big problem, and you need to control it very closely depending on where you're at. As you heard in my previous discussion, if you have an ionizable system, you literally have a 2-component system, and how much of each component is relevant to the pKa or the pKb, the ionization constant of that molecule. So the closer you are to the pKa value or the pKb value, which by definition is a 50-50 mixture of both ionizable components, the worse your problem is going to be. If you can think about an ionization curve, it's an S-shaped curve with the pKa or pKb right in the middle of the S. Therefore, the most change you're going to get is around the pKa value. So if your buffer system is right on top of the pKa or the ionization constant, you need to have a very good buffer, because a 1/10 of a pH unit change could lead to a 10% change in the distribution of the 2 ionic species. That's why if you're working with an ionizable compound, you want to make sure you're at least 2 pH units either on the low side of the ionization constant or on the high side. That will ensure that you're dealing with only 1 ionic species. If you need to work in the middle near the ionization constant, you just have to have a very good buffer so that your pH doesn't change during your assay.
Thank you. Let us proceed with the second part of the presentation. We have a few questions remaining, but we'll be answering them at the end of the presentation or via email, depending upon available time.
Before we get into the larger function of applications, we're going to take a look at spectral correction in fluorescence. This is equivalent to the background correction that you would do in a UV. Unfortunately, with a fluorometer, because it's not only a single beam instrument, the instrument is also blind to anything that doesn't luminesce. This means that it's very difficult to collect a background correction. So what you have to do is you have to collect the characteristics of the instrument wavelength dependent profile. From the top of this slide, you'll see the equations for the excitation. This consists of the light source characteristics and the excitation monochromator or the diffraction grating characteristics. For the emission side, it depends on the wavelength dependent detector changes and the emission monochromator. You see at the bottom an example of the instrument profile. You see it peaks at about 410, but you can see that there's a drastic difference in the emission side sensitivity as you go from 300 out to 800. Now, what this means from a practical point of view is that you just can't collect either an excitation or an emission spectra and compare it to an excitation or emission spectra from another fluorometer. They will be different. And this is shown here on the left-hand side of the slide. You see 2 different instrument profiles from 2 different instruments. You see that the profile on the left is different, that's kind of greenish gray, is different from the blue profile on the right. And you'll see how the underlying instrument profile that's different between the 2 instruments makes the peaks look different. In other words, in the first graph, the first peak is higher than the second peak, and it's the reverse in the blue peak, and this is because the instrument profile is different. If we do a spectral correction and correct out the wavelength-dependent differences of the instruments, you'll now see the corrected spectra on the bottom where the peaks are in their proper relationships to each other. Now, the left-hand side is a bit exaggerated. What's more realistic is what's on the right, where you see a quinine sulfate emission spectra. The red is the spectra after correction, whereas the black is the uncorrected. The reason that I went over this is to draw your attention to the fact that you must be doing spectral correction if you're going to be doing any type of work where you're going to need to compare with other instruments. The good news is that for the Shimatsu fluorometer, this is all done in real time and done automatically, so you just have to put the instrument in the corrected fluorescence mode, and then you will be generating corrected spectra. We're now going to take a look at measuring quantum yields. And basically, a quantum yield is nothing more than the efficiency at which a molecule emits fluorescence or phosphorescence, and it is a physical characteristic of the molecular structure. It's basically a measure of how bright or how efficient a molecule is at re-emitting light. It's typically a number between 0 and 1, with 1 being totally 100% efficient and 0 being non-luminescent. And you can see the equation is nothing more than a ratio of the photons emitted to the photons absorbed. We can measure quantum yields two different ways. Both of these ways require a corrected spectra, which is why we went over looking at corrected spectra first. A relative quantum yield requires a reference material of known quantum yields. The absolute quantum yield does not require a reference material, but it does require an integrating sphere. So it's kind of a trade-off. You can generate quantum yields either way. In general, an absolute quantum yield is considered a more precise measurement than a relative quantum yield. The reason being that relative quantum yields, your reference material must be in the same wavelength range as your material you're trying to calculate the quantum yield for. Now, a relative quantum yield is not a difficult measurement, but it has a lot of moving parts. What you need to make a relative quantum yield is you need a UV visible spectrophotometer and you need a fluorescence spectrophotometer. So you need two instruments. You need the corrected emission spectra. You need, as we talked about in the previous slide, a standard reference material, known quantum yield. And that standard material, the excitation for both the standard and the unknown must be the same. This means that the excitation spectra of both reference and unknown must overlap because you're going to have to use the same excitation wavelength to generate the emission spectra. And lastly, the emission spectra needs to be done very dilute. The absorbance should be less than 0.05 at the excitation wavelength. On the right, you can see a spectra of what we're going to be using here for our example system, where we have uranine as the standard measuring an unknown, which is rhodamine B. You see that the uranine has a quantum yield of 0.97. So here is our equation for a relative quantum yield. It looks a bit intimidating, but it's nothing more than some simple algebra. It is basically 4 ratios of the standard reference material against the unknown multiplied by the quantum yield of the standard. The 4 ratios include the absorbance measurement at the excitation wavelength, the peak area for the corrected emission peak, the refractive index of the solvent, and the dilution factor between your UV visible absorbance measurement and your emission measurement on the fluorometer. Now, the very good news in all of this is the software does all the heavy lifting for you. Here you see the output of a relative quantum yield measurement that we've been talking about. On the left are the emission spectra for the uranine standard and the rhodamine B unknown. The software calculates the peak area. Over on the right, you see the excitation spectra. The arrow shows you the excitation wavelength, which is about 495 for both the standard and the unknown. And then below that is the output of the calculation, where you can see it's calculated rhodamine B to have a quantum yield of about 0.715, which is in very nice agreement for the known value of rhodamine B. Now, for an absolute quantum yield, it's actually a much more simplistic measurement, but it does require a more expensive piece of equipment. It requires an integrating sphere that you see pictured on the right-hand side. You see the cuvette resting inside the integrating sphere. And the reason why this can be an absolute measurement is when you close the lid, all of the light that is emitted by the sample is collected by the sphere. And we're going to use the Rayleigh-Tyndall scatter peak and the emission peak as our photons in and photons out. You can see over on the left, for our blank measurement, we have a very large Rayleigh-Tyndall scatter peak at 1, and no, the solvent is not emitting anything, so there's nothing but a flat line for peak 2. The Rayleigh-Tyndall scatter peak for the sample is much smaller at 3, and then you see the emission peak at 4 for the emission of the sample. Over on the right, you can see that the photons absorbed is calculated from the Rayleigh-Tyndall scatter peak with 1 minus 3, the blank minus the sample Rayleigh-Tyndall, and then 4 minus 2, which is the sample emission minus the blank emission. So the mechanics of doing an absolute quantum yield, again, the software does all the heavy lifting. All you're doing is making 2 measurements of the solvent and the unknown, and then on the left-hand side, you see you set the range for the Rayleigh-Tyndall scatter and for the emission peak. You can see by the blue arrow down there, it's set for the range where the Rayleigh-Tyndall is at, and then the green arrow is where your emission is at. You'll notice that the Rayleigh-Tyndall for the blank is hugely off scale. If you look over on the right, you'll see we've rescaled things so that now that Rayleigh-Tyndall peak for the blank is now on scale, and you can see how small the peak is for the sample. But basically, after you set the ranges, the quantum yields drop out. It calculates the areas for you. It does all the math. The math is up in the upper left-hand side for those of you that want to dig into what it's actually doing. But basically, the software then gives you both an internal quantum efficiency and an external quantum efficiency that are right around 0.53, which is well within the accepted bounds of the known value for quinine sulfate, which is our unknown material here. So what can we use quantum yields for? They involve a fair amount of work to get at, but quantum yields are absolute. We talked before about fluorescence intensity units are relative and vary between instruments, but a quantum yield is like an absorbance unit. It's going to be the same no matter what instrument you measure it on. So it's a way of getting around the relative fluorescence intensity problem in reporting an absolute number. And they can be used for materials characterization. They can be used for characterizing the environmental effects on fluorophores, and they can be useful in investigating fluorescence quenching in life science or other types of assays. Our last 2 applications that we're going to look at are synchronous scanning spectroscopy and 3-dimensional spectroscopy. Synchronous scanning spectroscopy is where you lock the excitation and emission monochrometers together at a given offset and scan them both simultaneously. What does this do for you? It looks for the overlap between excitation and emission. If you look at spectrum A in this slide, you'll see the excitation, which is dashed, and the emission, which is solid, do indeed have an overlap there, kind of in the middle. This is what a synchronous scan is looking for. In general, a small offset results in simplification. A large offset results in increased complexity. So what this means is if you have a mixture and you do a synchronous scan at a small delta offset, you will get a simple peak for every component. For example, you can take benzene, toluene, and xylene, which are very close together in their fluorescence properties, and get almost baseline separated 3 synchronous scans peaks, which could actually be quantitated. So small delta offset synchronous scanning is very useful. Larger offset synchronous scanning results in increasing complexity or a fingerprint. In the bottom, you can see there's a blue arrow there showing that a larger delta lambda, or as you increase the delta lambda, it's as if you shifted the emission spectra to the left or to a shorter wavelength, indicated by the blue arrow. So as these peaks overlap, you get the red spectrum that's to the right of it, which is a synchronous scan at a larger offset where you're overlapping this vibrational structure, and this can be used then as a fingerprint. Very common technique in identifying different types of polyaromatic hydrocarbon mixtures like fuel oils. We will now consider three-dimensional spectroscopy, which is where you collect a number of emission spectra at different excitation wavelengths, and then the software can produce different types of plot of this matrix data. Stacked plots. Here you're looking at a contour plot where the dark lines or the colored lines connect areas of equal fluorescence intensity. This is by far the most common way of dealing with three-dimensional data, and it's kind of like reading an X-ray. You have to kind of get used to it, because in general, the more symmetrical the peaks are, the more they're probably only consistent of a single component. Here we're looking at a spectrum of milk. There look to be at least 2 major components in it, because there's 2 mountain ranges, as well as the one on the left is probably not a pure component because it has a degree of asymmetry to it. But you don't really know. This is why a synchronous scan usually yields more definitive information. But here we see the emission spectra is a horizontal slice through the three-dimensional matrix, whereas an excitation scan is a vertical slice denoted by the dashed line through the three-dimensional matrix. So what kind of slice through a three-dimensional matrix is a synchronous scan? Well, it's actually a diagonal slice. Here you see 2 three-dimensional matrices, and they're done in such a way that you can see the Rayleigh-Tyndall scatter peaks, and that's the diagonal line that's running through both of these presentations. The synchronous scan is a diagonal slice that is parallel with the Rayleigh-Tyndall scatter line, which is here denoted by the solid line, and a small delta offset is the dotted line, and a larger delta offset is the dashed line. The picture on the right is probably 1 fluorophore. The picture on the left is probably at least 2. And you can see how the synchronous scan would be fairly simple for the one on the right, whereas the one on the left that's 2 or more fluorophores, it would probably consist of more than a single peak. So I wanted to show you one slide where we put everything together. Here is a three-dimensional matrix contour plot showing you the 3 slices for an emission, an excitation, and a synchronous spectrum. You see those spectrums at different wavelengths for the emission at the top and for the excitation along the side of the contour plot. And then the synchronous scans are shown separately up above. And you can see, I don't want to get involved in the interpretation here, but there are certainly more than 1 component. There are clearly 2. And by looking at the synchronous scan and probably playing around, we're probably looking at maybe 4 components here. But the main takeaway from this is just to get an idea of how everything relates to each other between a contour plot and a synchronous scan. So here I wanted to show you that the generalized rules that I gave you at the beginning of this, the fact that small offset, simplification, large offset, leads to a more complex structure are just that, generalizations. Here on the lower figure here, the lower contour plot, at a offset of 70 nanometers, you still get a single peak. So this is clearly a simple one peak compound because it's going to give you a single synchronous peak both at small and large delta offsets. The figure above is clearly composed of two that you can see from the contour plot, and that kind of shows up in the large offset 55 and 130 delta offset synchronous scans. So you can see how using synchronous scanning and three-dimensional scanning kind of go together to extract the maximum amount of information. Here you see contour plots for three different varieties of milk. And milk can vary tremendously because whatever the cow is eating, you're probably eating as well, because whatever the cow eats kind of comes through to the milk. So most of the time what we're looking at are differences in butterfat content, which are your basic skim milk and 1%, 2% whole milk. So here you can see how that shows up in fluorescence spectroscopy. You can see we have the same two general peaks, but there are clearly minor differences in minor components between the three varieties. So we're going to finish the webcast by showing you how synchronous scanning can be used quantitatively. So here we see a mixture of three very complex polyaromatic hydrocarbons, pyrene, benzopyrene, and benzofluoranthene. The emission spectra is on the left, and as you can see, it's a peak fest. There's a lot of vibrational structure here, which is what you would expect of complex polyaromatic hydrocarbons like this. We've expanded the emission spectra. These were all collected at an excitation of 335. And unfortunately, the pyrene, which we want to quantitate, is very low intensity and shares a considerable overlap with the emission of the other two components. But if we take the maximum emission peak, which is at 382, and we subtract the excitation wavelength of 335 from that, we get 47. So stay tuned for the next slide. So we're now going to take that difference that we calculated from the previous slide, which was 47, and we're now going to make that the delta offset for a synchronous scan. And you can see the synchronous scan of the mixture over on the left, and you can see that with the judicious use of the correct delta offset, we've managed to isolate the pyrene, which is the red spectrum there, which is nicely separated from the two other components in the mixture. If we then measure three different concentrations and calculate the area underneath the synchronous scan peak for pyrene between 361 and 391, we wind up with the quantitation data that you see presented on the right, where we plotted the area against concentration. You see we have a 0.999 correlation coefficient. So there we're going to finish up with the fact that you can use synchronous scans to actually quantitate complex mixtures if you can figure out the right delta offset to use.
Dr. Taylor, thank you very much for such an exciting presentation, and thank you to our audience for attending and sending questions. We'll now answer your questions. I think we have time for a couple of questions. We'll try to get as many done as possible. The first question I have is, for relative quantum yields, why do you use the full width at half maximum area rather than the total peak area?
Okay. This is because of a unique feature of fluorescence peaks. Fluorescence emissions are not terribly symmetrical. Even if you have only a single peak, you'll notice that the peak tails off into the red. It's not Gaussian in that it has a uniform symmetry. It tends to kind of tail and drag into the red. So the reason why we use the full width at half maximum is it is a good way of getting just the center core of the peak. It's better than a peak height. but it might not be subject to problems that you'd have with the peak tailing out into the red. So it's just a slightly different form of area that is less subject to artifacts from sample to sample.
Thank you. The next question is, here you go. What method is better for mixers, 3D matrix or synchronous scan?
Almost a trick question. They are two techniques that measure the same thing but can provide you with different information. So I'd be hard-pressed to say one is better than the other. They are actually complementary techniques. And most people that are doing mixture analysis or things like this would probably use both. Synchronous scanning gives you more definitive information in that it's a single scan and it's easy to analyze. For example, we showed you how you could quantitate the area under it. Three-dimensional gives you a larger view of what's going on in its entirety, but it takes longer. You have to collect a series of scans. But the data can be somewhat difficult to read. Like I mentioned, it's a bit like reading an X-ray. You have to get used to how peaks become asymmetrical and how mixtures can sometimes form together before you can really read anything. And it's very difficult to quantize information from a three-dimensional, but it gives you a very good conceptual, qualitative view of what's going on. So I would say I would tend to use synchronous scanning when I had to produce a number. For example, if I'm going to quantitate or I need to know maybe a good idea of the number of components that are involved, I tend to use a synchronous. But I would probably then also do a three-dimensional if I had the time to confirm what I saw in the synchronous with what I saw in the 3D. So they really complement each other, and it's useful to use both.
Thank you. That was very helpful. Looks like we're at the end of our allocated time for the webinar. I'd like to thank you for all the interesting questions. Since we don't have time to answer remaining questions, we'll reach out individually to all of you whose questions we are not able to answer today. Once again, thank you all for attending and participating. We'll send you an email with a link to view a recorded version of this presentation anytime. We hope to have you back in webinars we organize in the future. Have a great day. Thank you.